In today's experiment, we'll study the infrared radiation, the IR, in the range of wavelengths of those wavelengths that are emitted by the hot Earth. As we know, the Earth takes heat from the Sun and emits this heat towards the space by IR, by far IR, having wavelengths of the order of a few tenths of micrometers. Here is our apparatus. Consists of two parts. One part is that part which emits the IR. The other is the part that senses the IR. The IR is emitted by this aluminium board, which is attached to a halogen spot. This is a 50 watts halogen spot. And this halogen spot hits the aluminum board. We have put a thermometer here. Here is the probe of the thermometer to measure the temperature of the board. We see now that it has a temperature of 49 degrees Celsius. The other part is the sensor. The sensor is here. This is the sensor. This is a PIR sensor. This sensor is connected to this circuit. This is an amplifier and also a low-pass filter. And the output goes to this digital oscilloscope. The PIR sensor measures the changes in the IR flux. That is, it doesn't measure the IR flux itself, only measures when it changes. Let's do an experiment to see how we can measure the changes of IR in this oscilloscope. Now, the sensor takes IR from the aluminum board, and I start the oscilloscope and put this beam blocker, a piece of paper. We note there is a small negative peak of the curve, and now I take apart the beam blocker. And now, after taking apart the blocker, a new positive peak appeared. So the first peak, the negative peak, measures the reduction in the IR when I put between the sensor and the board this beam stopper, and the other, the positive peak, shows the increase in IR when I remove this beam blocker. The voltage difference between the two peaks is a measure of the IR which passes through the sensor. There is also a second curve, this purple curve. This purple curve is the same as the yellow curve, but is filtered. It has taken out the noise. So there are two filters. One is the electronic filter, which is connected to the PIR sensor, and the other is the oscilloscope filter. So that we have a very well filtered output. And we measure the peak-to-peak voltage of the purple curve. This is shown here which is the value here of the peak?
2.04.
It is 2.04 volts. So this is a measure of the IR which hits the sensor. And now I will put successively the three transparent materials. First we put this material. This is a case of cookies. Made from plastic, probably plexiglas, but it's very thin. Now, start the oscilloscope. As before, I put a pin blocker. The curve goes on straight without making any peaks. I take the pin blocker apart and still no peaks. Just a straight line. So the peak-to-peak voltage difference is 0 volts. This means that no IR passes from the aluminum board to the sensor. Now I'll check this ruler, which is made from plexiglas. I put the ruler above the sensor. I start the oscilloscope and put again the beam blocker. Again, there is no depart from straight line, no peaks, no negative peak. Take the beam blocker apart, and no positive peak. So also the beam blocker is opaque IR. Now I test from transparency this vase made of glass. I put the oscilloscope on and put in between the beam blocker. Again, the curve is still a straight line, no peaks. Take apart the beam blocker, there are no peaks, no IR. I remove the glass and I repeat the same experiment with no other material between the board and the sensor. Press start and put the beam blocker. I see the negative peak. Take apart the beam blocker, see the positive peak. So what is the conclusion? The conclusion is that the usual transparent materials like glass or plexiglass are opaque to IR. The range of wavelengths of those emitted by the hot earth in a temperature near 50 degrees Celsius. And this completes the experiment. We made this experiment today, the 14th of June 2024, in this laboratory of digital electronics of the Department of Physics of the University of Ioannina. Many thanks to Dimitris. Thank you, Dimitris.
Thank you, Nikos.